to take a little bit of time off and to recharge those batteries and to rest your mind a little bit there. Okay, just a quick review here on two force members. We were talking and looking at this picture right here. We're going to continue talking about two force members, but I just wanted to reiterate the importance for us in statics is that first we need to be able to identify those two force members. This hydraulic cylinder right here is a two force member because it's only two locations with forces. That's all that means. That's all we have to be able to do is say, how many locations of forces does it have? It doesn't matter how many locations or how many forces are each location. It just matters how many locations there are with forces. When that happens, we know that the line of action has to go between those two locations where the forces occur. So even though at B, and they tell us that B is a pin here, by a pin at A and a pin connected to BC. So even though this B is a pin right here, and we talked about, oh, pin can have a BX and it can have a BY. Well, yes, it has an X and a Y component, but we know what angle it's at. And so when we draw our FBD, we need to be able to identify those two force members and then say, oh, okay, well, that means it's only one unknown. So when we draw that FBD, it's just this force in B to C. Now, if we look at our total number of unknowns, we have AX, AY, and the force in FBC. So only three unknowns. If we had drawn it as a BX and a BY, we would have four unknowns. We only have three equations of equilibrium, so we cannot solve it if it has four unknowns. We need to make sure that we only have four, or that we have less than four unknowns, that we have three unknowns in our problems. And so that's why we need to be able to identify those two force members. See a question here, when is the next hands-on? There's a hands-on going on right now. Hands-on number 4 is going to start next week. Oh, here's a two force member in real life, very similar to the picture we just looked at with the dump truck. I actually followed this truck home one day because I was like, I bet there's a two force member on there and I want to take a picture of it. Dumping it, I didn't have to follow it very far, but this is pin connected here, and you can't see it, but there's a pin connection up here. And so look at that big long hydraulic cylinder. That's a two force member right there. And so we can now start to figure out what the force in that two force member is. That's a tandem dump truck. Those usually carry about 10, they can carry about 10 cubic yards. It's a 10-yard dump truck in there. For a load of gravel, that could be anywhere between about 12 to 14 tons in there. So think about all the force that's actually occurring in that two force member. We'll start to look at problems and how we actually solve that and figure out what the force in that two force member is. And actually, before we go into 2D rigid body equilibrium, I want to go back and pick up where we left off. There's just one more thing that I want to talk about here very briefly from yesterday. Where is it? Okay, yeah, this is the static stability, redundancy, and statically indeterminate systems. For example, if we had a system like this that was a roller at A and a roller over here at B, well, that's not stable. That's a skateboard, right? So that's unstable. It's not properly constrained. It is determinate. Determinate just means that we can solve for those unknowns. So we could fix this and by adding a pin over here at A. Now it's stable, it's properly constrained, and it's determinate. And then what if I added one more connection though? What if I said, okay, well, let me add a roller at a new point right here. Well, I have four unknowns. This is what we call indeterminate. Indeterminate basically means that we cannot determine the values of those reaction forces with statics. You'll actually learn more about this in mechanics of materials. We're not really going to see this on the homework. Not really going to see this showing up too much. But for 2D stuff, We will talk about it some more with 3D stuff. But I just wanted to point out that, right, if we have too many unknowns, then we can't solve it with static. So we have a limited number of unknowns that we can solve using our static stuff. Okay. So back now. Oh, I was right there where I needed to be. Okay. So for today, we're going to continue with 2D rigid body equilibrium, but focus on solving. So using our 3 equations to solve for 3 unknowns. So our learning objectives are to identify all the rigid objects and which are 2 force members. So that's really important, and we'll continue talking about the 2 force versus the multi-force stuff. Then once we can identify all the rigid objects, that basically provides our list of options for free body diagrams. We can then take those options and pick the correct FBD to solve for specific support reactions or geometry. Think about these static problems, and we've been talking about this as identifying all the possible options. It's kind of like when you picked your college that you were going to go to. Most people probably didn't say, I'm only applying to Mines and I'm just going to go to Mines. If I don't go to Mines, I'm not going to go to college, right? You probably had some other schools that you applied to, and you identified all the options, right? You're like, okay, here's option A and it has this major and it doesn't have this, but here's option B and it has these, things associated with it. And here's option C. And then once you have your options A, B, and C, then you can say, well, you can start narrowing down each of those options and picking the right one, the right college for you. Well, we're going to do the same thing with free body diagrams, where we need to be able to identify all of our possible options, all the rigid objects, and then we can pick the correct one. Once we draw the FBD, now it's really the easy part, and that's using those 3 equations of equilibrium to solve for those unknowns. And then also we'll look at identifying which equation should be used first, second, and third. So there are some definitely some keys there that we can think about. So again, options, even with our equations, it's options, right? It's like we have 3 equations. Well, what's our first option? What's our second option? What's our third option? And just going through those options, but we have to identify them first. You do have a homework problem here where you're going to be asked to draw FBDs in Mastering Engineering. Starting at the black dots is what it says to do, and that means the tail of the arrow is at the black dot. Be picky with your orientation and your starting point. They ask you to draw the FBD of this rigid object right there. Notice this D to C, how many locations does it have with forces? Only 2. It's a 2 force member. How about this rigid object, AC to B? That has 3 locations. And so that's a multi-force member. Okay, here's the second homework problem here. We see a distributed load. We're asked to find the support reactions at the roller at A and the pin over here at B. Another homework problem here. In this one, the sign convention is provided in the problem statement. So make sure you follow that so that you use a negative when you should have used a positive, or vice versa. In this one at A, this is a fixed support. And they're asking us to find what are the reactions at that fixed support. So remember, we can figure out what to include in our FBD at A based on what that fixed support is allowing and what it's preventing from happening. It's preventing translation in the X and the Y direction, and it's also preventing rotation, so it has a moment. While a pin at B in this last homework problem, it allows rotation to happen, so there's no moment at B. There's no reaction moment at B because there's nothing preventing it rotating at point B. The system together with the roller and a pin, that prevents the object from rotating, but there's no moment reactions at either of those supports. And then the last homework problem here is asking us to find theta. And I have a question for you all. Is AB a 2 force member? Well, how many locations do we have with forces? We have A is 1 location and B is another location. So there's only 2 locations, but there's a moment. Okay, so that means it's a multi-force member. All right, we don't know the line of action. The line of action does not go from A to B. So even though there's only two locations, anytime we have a moment, that means it's not a two-force member. And that can be an applied moment, like we have here, that 50 Newton meters down at A. It could also be a reaction moment at a fixed support as well. Okay. All right, let's jump up to the board and let's do a example here of a problem with a fixed support. So we have a beam, and actually I came up with this example based on the overhang on the west side of Marcus Hall. There's that big long overhang, and actually after we get snow, like we did on Wednesday, the snow ends up dripping off the edge of that thing, and they have to like put cones and like block it off so people can't walk out there and stuff. So the design is not very good, but it looks really cool, right? Well, let's look at how much, if that cantilever there, so it's just kind of overhanging, a cantilever is an overhang. If it had a distributed load, let's say the snow piled up on it like this, where maybe over here, W1 is equal to 1,000 pounds per foot. And then on this end, W2 is equal to 1,500 pounds per foot right there. At point A, this is a fixed support. So basically meaning that it prevents translation in both directions. It prevents rotation in both directions. Yeah, right. There's a load bearing. So Brent's asking, isn't there a load bearing glass door in Marcus that you can't open or else the building might collapse? I don't know if the building will collapse, but maybe it has something to do with HVAC or I'm not sure. That sounds like a nice rumor though. Okay, so A is a fixed support, and we can show that. And I'm going to show that on paper and by doing kind of some like little dash lines here. That's showing that, oh, you know what? This is a solid wall that we're connected to. And so it's buried. We're buried into that wall right there. Let me draw a few more arrows in our distributed load. Just remember the number of arrows doesn't matter, but the length of the arrows is representative of the magnitude. And then that span, it's a pretty good span. I'd say it's about 15 feet or so. So let's say at 15 feet, well, what are the reactions? What we want to find for this problem is the reactions at A. So what did they have to design for that overhang there? What did they have to design it to resist? And so we take those reactions, the reaction that we're going to find, that's what the material would have to resist. Now that's where we stop in statics, is we calculate the reactions. We don't go into like how the material is going to resist that. That's what you'll start looking at when you get into mechanics of materials or solid mechanics. Okay, so our solution, what are we going to start with? If we're doing rigid body equilibrium, what is always going to be our first step? FBD, yes, Luke, thank you, right? Yeah, we're always going to start with an FBD. And in this case, what do we really have for our FBD? We really have the FBD of the whole thing. And so let's see, we called that A on the left there. Let me go ahead and add a label. We'll call this B over here. So we're going to do an FBD of AB, of that whole thing there. So let's see, we have basically we're removing the fixed support there. And so we just have our beam that's sitting there. It's got this load, and I'm going to just draw the original distributed load on there. It's got this distributed load, and this is W2 equal to 1,500 pounds per foot. I've got a W1 that's 1,000 pounds per foot over here. And then we have this span of 15 feet. And so there's our rigid object. And we're going to right now we're always going to draw free body diagrams of the entire rigid object. So that's the entire rigid object. We're just cutting it off at the support, right? The support is where it's connected to the rest of the building, in this case right here. Now, what is that support preventing from happening? If we have a fixed support, is it allowed to rotate? No, so there's a moment. Is it allowed to translate in the X? No, so there's an X force. Is it allowed to translate in the Y? No, that fixed support, right, it'd be like me holding onto this really tight. That fixed support is preventing all that stuff. But then I remove the fixed support and I have to replace that physical fixed support with the forces and moments. That's my model. It really doesn't matter what direction we draw stuff in. Like for example, my moment right here, my moment reaction, I could draw it clockwise or counterclockwise. We could think about what it's trying to do, right? If it's going like this, then isn't that reaction trying to hold it back into place? And so we can do that, but we don't necessarily have to. So I'll draw MA going counterclockwise there. And then I'm just going to pick a direction for AX. So there's my AX. And I'm just going to draw AY going up. So there's our support reactions. And now we have our completed FBD. We're done with our FBD, essentially. We can now start, looking at our equations, summing forces and summing moments. Now, when we start doing that, though, when we start summing forces and moments, we are going to want to what our concentrated forces is. And so we covered distributed loads before. So we're going to have, from this trapezoidal distributed load, we're going to have, I'm going to call it an FR1, and we will have an FR2. And we can figure out where those are located because they're at the centroid of the shape. And so like FR1 would be at a distance here of 2/3 of that 15 feet. And then FR1 would be at 1/2 of that 15 feet. So we know where FR1 is located. We know where FR2 is located. Unlike our quiz, we do not need to figure out where the total resultant force is located. Because I can take moments now. I can sum forces now. I can leave those as two different concentrated forces. I don't need to resolve them into one in order to solve the problem. Unless they specifically asked me to. Unless they said, you know what, you need to resolve those forces into one force. And that's one of the things I'm asking you for. But they're not. They're just asking us for the reactions at A. And I can determine the reactions at A if I have an FR1 and an FR2. So let's see. We can now go into, let's just go through the equation. Sum of forces in X is equal to 0. I'm going to define my positive going to the right. Let's see, I've got an AX. That's the only thing I have in the X direction. So AX is equal to 0. We can now jump into sum of forces in the Y is equal to 0. If I sum forces in the Y, let's make our positive going up. I'm going to have a positive AY, a minus FR1 minus FR2 is equal to 0. So AY is going to be equal to FR1 plus FR2 when I solve that algebraically. Oh, and it looks like we haven't figured out FR1 and FR2. Let's see, FR1 is going to be the area of the rectangle, which would be 1,000 pounds per foot times that total 15-foot distance, which gives us 15,000 pounds. FR2 is going to be the area of the triangle, 1/2. The height of the triangle is only 500 pounds per foot times 15 feet. And this is going to give us 3,750 pounds. So now we can solve for AY. AY is going to be equal to 18,750 pounds. Okay, so we found AY. That would be the force that's holding up that cantilever, right? When we have 18,750 pounds going down, well, we have to have 18,750 pounds holding that thing in place. Now, how about the last equation we have is to find MA. And we're going to sum moments. And we have to pick, where do we want to sum moments about? We can really sum moments anywhere. But which point is going to get rid of the most unknowns? Well, point A is going to get rid of the most unknowns. So I'm going to sum moments about A is equal to 0. Now, this is different than my moment about A. So the sum of the moments about A, that's stating what equation I'm doing. The moment about A is the reaction moment that's at that fixed support. We'll assign our positive sign convention like we've done before, where counterclockwise will be positive. So I have MA is causing a moment in my FBD. I have a couple moment. That reaction moment at MA is a couple moment. It's causing a reaction of MA. It's going counterclockwise, so it's positive. Then we have FR1. That is causing about point A negative rotation at a distance of 7.5 feet. We also have a negative FR2 at a distance of 2/3 of 15 would be 10 feet. And we would set that equal to 0. Also notice that I am writing my equilibrium equations with everything on the left-hand side and only equals 0 on the right-hand side. I save my algebra for the next step. And then I see a question in the chat here. How do we know the direction of the moment? We don't. I mean, we could like try to think about it conceptually. And, you know, if we think about it conceptually, it's going like the forces are trying to do this. And so our moment has to pull it back this way. So our moment is doing that. But if I drew it in the other direction, what would happen? I would just have to throw a negative sign in front of this. And then I would find a negative moment for my answer. And it tells me it goes the opposite direction that I drew it. So it doesn't matter what direction we draw it in. We can draw it in either direction. Our equation will tell us what direction it's going in. Now in this one, when we do our algebra, MA is going to be equal to a minus FR1 is 15,000. Let me draw. Minus 15,000 times 7.5 feet minus 3,750 times 10 feet. Oh wait, but I moved them over to the other side, so doesn't that mean that these are both positive? I have a positive and a positive. So I find that MA is equal to a positive 150,000 foot-pounds. So I found a positive number, which means that it goes in the same direction as drawn. Question. Any questions about that? So what would happen if I drew it in the other direction? Wouldn't we find a negative number? And then what did that tell us? It goes the opposite direction, which in the end we would get, regardless of what direction we drew it in, we would get a counterclockwise direction as the result, wouldn't we? Okay. Any questions about that? Same thing for AY. Imagine, what if I drew AY going down? Nothing wrong with that. If I drew AY going down, wouldn't I find a negative number for AY, which just tells me, oh, you know what? It needs to go it needs to go up, not down. So we can pick any direction for our reaction forces. The math will work it out for us. And then, would we ever have to include the weight of the beam? Yeah, we could ask you to include the weight of the beam. In this class, though, if we don't tell you the weight of the beam, just assume that it's 0. In real life, absolutely, we would include the weight of the structure in this calculation. The weight of the structure, depending on what we're looking at in the scenario, sometimes is pretty small. And so for us, it's reasonable to neglect the weight of the structure and not consider it, and still, do this and get an answer that means something. But good question. Yeah, sometimes we will give you the weight of things sometimes, but if we don't, just assume that it's 0 or negligible. Okay, let's go on to a problem with a little bit more going on now. So we have this articulated crane boom, and it has a weight of 125 pounds, a center of gravity at G. Oh, there we go. We've got a problem with the weight in it. I didn't even think about that when you asked that question. So nice segue. It supports a load of 600 pounds. Determine the force acting at the pin A and the force in the hydraulic cylinder BC when the boom is in the position shown. Now, they just kind of show stuff over here. Notice how it's just kind of disappearing off the page. When we write our given information, which is what we're going to do right now, we're going to redraw all this stuff. And they tell us that BC is the hydraulic cylinder, which means that isn't there another pin over here? And I'll draw, when we give this, I'm going to draw another pin. We're going to say pin, C is a pin, right? Because hydraulic cylinders, they have to be connected by things that don't have moments, because they need to be two force members, don't they? So let's go ahead and let's start drawing our given information. Now, as our problems get more complicated, I found one way to draw things nicely and have the relative locations of things show up at the right spot is to first draw our points. Instead of going right in and drawing the physical objects, like what if I drew, what if point A was right here? Well, let's see, that puts like point B maybe is like right there. We can put a point G at about right there. And then what if we put the load at about like that spot right there? Now we can draw, this is our rigid object, or this whole thing right here is one solid rigid object right there. So now we can draw that, and it captures all those points. Now how about some of the other points? Well, let me see. Point C, let me draw point C. Oh, I don't know, maybe that's going to be about right there. And then I'm going to make a point D. It's not on our picture over here, but I'm going to do a point D, and we'll do that point D at about right there. Now we know that we do have this hydraulic cylinder that goes from B to C. So I'll go ahead and draw that. That's one rigid object right there. I'm going to do this little triangle thing to show that point C is a pin. And in this case, I'm just calling it a pin support there. Point D right here, I'm actually going to show, and we can draw the rigid object that goes around there. And I'm actually going to show point D. They don't show us how it ends, but I'm going to say point D is a fixed support. So I'm adding that to our problem statement here. So point D is a fixed support right there. So actually let's not draw a little dot there then. Let's just do it like that. So point D is a fixed support right there. Okay, and then they tell us that we have 125 pounds right here at point G. I guess I could label that point G. I'll label my points here in a second. And then it supports a load of 600 pounds. So here's our 600 pounds. And actually, before we do all of our labels on our points here, let's show some dimensions. And they tell us that like this dimension from there to, actually I'm going to do it a little bit differently. Let's go from there to there. That's 1 foot. This next distance then is 3 feet. And then this last distance here is 5 feet. So I'm just going to show all the horizontal dimensions on one line there. And then they also tell us that the vertical distance right here is 1 foot as well, right? That's that 1 foot right there. And let's see, there's one more thing that they tell us. They tell us that this is an angle of 40 degrees. And what they want us to find, so that's all of our, oh wait, we need to, I said I was going to add the point labels here. And we need those for sure. A, B, G. This was point C. Oh, we labeled that point C already. Point D we already labeled. And then why don't we call this, let's see, A, B, C, D, E. Why don't we call this point all the way out here at the end? I'm just going to call that point E. And so we want to find the force at pin A and in the hydraulic cylinder BC. So all of a sudden now it's kind of like, holy cow, there's a lot going on, isn't there? We have like two forces. We've got like a pin connection at A. There's a pin connection at B. There's a hydraulic cylinder. But let's look at how we can break this problem down into steps that we can use for any problem in 2D rigid body equilibrium stuff. In general, I have found that these steps work really well. And so that is to first, number one, is to identify all the rigid objects. Next, we can consider FBDs of each rigid object. Number three, we'll pick an FBD with knowns and not too many unknowns. What is too many unknowns for us? If we're in 2D, it's based on the number of equations that we have. And how many equations do we have here? Let me get somebody going from the front row here. How about Kaylee LaRue? How many is too many unknowns? How many equations do we have? How many equations do we use on the last problem to solve it?
Like three?
Three, yeah, right? Because we have sum of force in the x, sum of force in the y, and sum of the moment. So we have three equations, which means three unknowns is okay, but four is too many. Okay, excellent, thank you. And then step four, this is really the easy part. This is implementing those equations, sum of force in the x, sum of force in the y, and the sum of the moment equation. Okay, so there's our steps. And actually, I'm going to grab those and I'm going to move them over to there so we can start filling in some, we can see our picture still, so we can stay close to our picture. I'm going to continue moving those steps out of the way here. Okay, so there's our steps that we're going to follow. So let's identify all of our rigid objects. And so what are all of our rigid objects for this problem? So you don't have to move your steps over, right? You can leave it where it is. I just want to be able to see the picture still. So like, what's one of our rigid objects? Oh, DA. Yeah, I have DA. That's a, yep, absolutely. I'm going to call it AD. Doesn't matter what you call it. And then I see ABGE. Yep, that's another rigid object. ABGE. It just means that they're all one solid piece. Okay, that's the only thing that means, is identifying rigid object just means it's all one solid piece of steel or wood or whatever the material is. And then there's one more. There's BC. Okay, so we identified all the rigid objects, but now let's list their type. What type of rigid object is AD? Is it two force or is it a multi-force? How about somebody else from the front row? Ted Kim. Ted, AD, is it two force or is it multi-force? And just take a guess if you want to. Is Ted here? Maybe Ted's not here. We only have 45 people today. Oh my gosh, where is everybody? For those of you that are here, nice work for signing on and sticking with us. Okay, it is a multi-force. Luke, yes, absolutely. The reason it's a multi-force is even though it has two locations, it only has two locations, it meets that criteria, it is a fixed support, so it has a moment. ABGE is also a multi-force, and the reason is because there's 1, 2, 3, 4 locations with forces. BC is a two force, so I'm going to shorthand this as 2FM. So which one of those then? So now that we have our rigid objects listed out, let's think about those. A to D, does it have any known values? No. B to C, does it have any known values? No. Which one is the only one that has known values? It's ABGE, right? This is the only one with knowns. And so that keys us in almost in every statics problem. We have to start with knowns. If we don't have knowns, we can't solve for the unknowns. Think about those known forces as kind of like these big arrows pointing and being like, hey, pick me, pick me. I'm the one that you want to pick. Now, the other thing about identifying our rigid objects here, though, is that it also keys us into what we are going to have at our at the locations of our connections. So we are going to do the FBD of ABGE. And I am just going to draw this as a wireframe now. I don't need to draw any of the like thickness of that thing or anything like that. I can just do, it's an L shape right there. We do know that we have at point G, we have 125 pounds. We have 600 pounds out here on the end of this thing. And we have these pin supports at A, and we've got a pin support right here at B. So what are we going to put there? How many unknowns? Because we're still really, we haven't talked about how many unknowns this is going to have. Hopefully it doesn't have too many unknowns, right? Correct. Okay. And so, Kala, have you heard that part now? Was that okay? Okay. So A is, well, actually, let's start with B. So point B, this is a two force member. So it's going to have an X and a Y component, but don't we know that the line of action has to go between those 2 points where the forces occur? So it has to go between B and C. I don't know what direction it should go in. I'm just going to pick down and to the left. So that's just one unknown. FBC. At A, that is a multi-force connected to another multi-force. I don't know where the line of action goes. So it's only when we know where the line of action goes do we draw it as an FBC. Now at A, I'm going to do this as an AX and an AY. And again, I'm not really worried about what direction I'm drawing them in. I'm just arbitrarily picking here. I can pick any direction because my math will tell me if it needs to go in the opposite direction. So we have an AX and AY. There's our three unknowns. We've got AX, AY, and FBC for this problem. We have known values. We can add our geometry here. Like we know this distance right there is 1 foot. We've got our horizontal distances here. 1 foot, that's 3 feet. And this last one here is 5 feet. So I know my scale is off a little bit, but that really doesn't matter. 1 foot, 3 foot, 5 feet, 1 foot there. Oh, and then we also know that this angle right here is 40 degrees. So now we have an FBD with three unknowns. We have our three equations of equilibrium, but let's think about here, and then we'll stop for the day, but let's just think, what equation are we going to use first? We could do sum of forces in the X. How many unknowns would that have in it? It would have AX and it would have FBC, wouldn't it? Because FBC has an X component, so that has two unknowns. I ultimately, as an engineer, I don't want to do more math than I have to. I mean, engineers love math, right? But like, you know, we want to keep it as simple as we can to reduce the mistakes. So I'm ultimately looking for one equation with one unknown. Sum of forces in the X has two unknowns. Sum of forces in the Y will also have two unknowns. The sum of the moment equation, though, if I pick a good spot, I can get rid of all but one. Which spot, anyone in the chat, which spot should I take moments at in order to get rid of all of my equations, or all of my unknowns, but one? At point A. Right, because A has two unknowns. If I sum moments about A, AX and AY do not cause any moment about A, so they evaporate from our equation. So we're going to sum moments about A is equal to 0, and we will do that when we come back on Monday. You all have a great rest of your Friday. Have a great weekend, and we'll see you on Monday.